Hello, everyone. In today's lecture, we will learn a new two Python libraries. The first library is Pandas, which is allow us to make our computer to import and export files such as Excel to your Python script. The other library is basically important machine learning library, which is sklearn. Before go that, let's also try to know a new type of file, which is very close to Excel sheet. Now, usually Excel sheet is very heavy, and we want to find a lighter version for that. So you can go with a save, and basically instead of save it as an Excel work, one of the files will be a CSV or comma delimited file, and you will see it executes all the options that are available in Excel. And if you want to take a look to the space, so these both data have the same name, but this is what was as a CSV file, the other one as Excel file. So this is basically 10 kilobyte versus the other one is only 1 kilobyte. Now, it's good to basically go through the data and see how it look like. So we can draw a simple line and see how it fits. So if you draw a scatter diagram using Excel and add a trend, and Excel allows you to select different type of trends. So I can comfortably go with the linear regression. Now, if we go to the exponential, it won't go perfectly, but there is a one missing point. Of course, missing one point is not important, but if we have a more like than this one, such as this scenario, so we can try to avoid this kind of thing. Here, for the second degree, order of polynomial, power, moving average, etc. So we can stick with the linear one. Open now your shell and run the Jupyter notebook. When you run the shell inside the file, so the directory by default will be the same file that you have run the shell. Open a new notebook. So I might be already installed the pandas and the sklearn files, but doesn't harm to go with them again. Pip install pandas, and we are gonna run it. So it will give me a warning that the file is already installed there. Then we will have pip install sklearn, and I think it's already there. It's already there, and we can now proceed. So let's install our the libraries that we're gonna use in our Python. So we're gonna call the NumPy library. So import NumPy as an NP. Then import pandas as a BD. Now, there is a multiple functions that we will call them from the sklearn, and each one of them will be serving a different purpose. From sklearn dot model underscore selection, we want to import train, test, and split. Now, it's very important you want to split the data sets. We will basically talk about it later with another type of data that needs transformation. Now, this one we will call the linear regression. So sklearn dot linear underscore model, and we want to import linear regression. So there is no space or underscore between them, and both of the words have a capital letter when they started up. And finally, we will assess or evaluate our models through mean square error. So the mean square error is basically the summation of the difference between the actual data set and the predicted. So from, again, sklearn dot metrics, we want to import the mean square error. So mean squared error. Now, the best value for mean square error usually is 0, but it is not bounded, doesn't have upper bound. There is another one which is more normalized. So the values for this one is between 0 and 1, which is the coefficient of determination. Coefficient of determination tell you to what extent the data or the model can explain variation on the target or Y using the feature X. So R2 underscore score. When this value reaches 1, meaning that we have a good chance that the features will explain the variation in the target. While when it's closer to 0, that meaning our feature cannot explain much about the change in the target. Now, finally, we want to plot the relationship between the actual data set, which is from the testing data set, and we want to compare it with the predicted model. So from mat plots library.py plot as a PLT. Sorry, so this is import. Let's call our data set first. So extract the data sets. So we want to import it. Let's call it data equals bd dot read CSV file, and you want to type it with its extension. So this will be data.csv. Now we want to define the features, which is X. So X equals data, and then square brackets with the title of this column, which is X dot values. Now, if you are using polyfit, you can go straight ahead to Y. If you are using multi-dimension features, it's okay to stick with this. But for now, this one, we need to reshape it. So reshape between -1 and 1, which will add us one column. And this is very important to determine the constant. Now we have Y, which is data, and Y. And we have the values, dot values, and you don't need to reshape this guy. Now we want to split the data set, which is very important, and we want to shovel it. Because each time we have a fold of data set, we might be getting a different answer, and selecting a different kind of models will end up fitting the best model here. Of course, we're gonna try to avoid underfitting and overfitting a problem. But for the simplicity here, we will select the model that have the best MSE or the minimized MSE with the maximized R square. So here, split data into training and test data sets. And usually when you're doing that, you do it with order. So we have X train, then X test. Regardless what you have named them, you should stick with the order. Then Y train and Y test. And then we call the function, which is a train underscore test underscore split. And when you open the banana bracket, you're going to add what data you're going to split. So X and Y. Now we want to see what is the size of our test. In wonderful world, we could split it into 50-50%, which will allow us to reduce the variance. But like if we have a small data set and there is many other factors could be play around, so it's recommended with the starting with or 80-20% split. And also it depends if you have a validation data set. So if you have a validation data set, then you're going to split it into 70% as a training, 10% validation, and 20% testing. So it depends on the problem. Now we want to basically have a fixed seed because each time we run the model without fixing the seed, we'll get a different answer. And we might be having the best model. So we don't want to throw this model away. So we have a random state, which is equal 1, 2, and 3. And now we want to build the model. So we want to build the model using the linear regression. And you can call the model as you wish. So model 1 with model 2. Here we have only one model. So model equals calling the linear regression. And you open and close the banana bracket. And now you want to fit the model on the training dataset. So the model parameters will be optimized basically by trying to minimize the mean square error for the Y train using the features of X train. So model dot fit X train versus Y train. After we have built the model, we want to see the prediction. So here, the prediction, or let's see the parameters of the model. Parameters of the model. So this model is simply Y equals A by X plus B. And since we have that, so we want to determine A equals model dot coefficient underscore, and then we have B equals model dot intercept underscore. Now we want to print these guys, print the slope, which is A, and then we want to print the constant, which is B. After doing that, we will try to predict our tested data set. So predict the testing data set. So Y predict will equals to model dot predict. Now it will be with X test this time. After that, you want to evaluate your model. So model evaluation. So we have the mean squared error equals mean squared error. And this time between the Y test and Y predicts. Again, we want also to see how it perform as a coefficient of determination. So R squared equals R2 underscore score between, again, the same values Y test and Y predict. Also, another good way to see how the model is performed is to visualize that through the scatter diagram. So scatter diagram for this data set. So we have PLT for the original data between X test and Y tests. And we're gonna add a label for that, which is original data. And we have also for the prediction, scatter X test again, but this time versus Y prediction. And we need to add a color. Well, this might be not important, but maybe if you have a different models, you need to see like how each model performs. So model will be in color red. And now we can add the label. Predicted data. After doing that, let's add the labels, X label for X axis and Y label for Y axis. And we can add a legend. And finally, we want to show the plots. And you can execute the model here. So you can see that we like have a very good fit. So the slope was 2.4. The constant was 81. So our equation will be simply y equals 2.4 by x plus 81. Yeah, I have also forget to print the MSE. Let's see here. Yeah, let's add them. Print the mean square error to see how well this model performed, and print the R square. So for this model, the MSE was 1,689, while the R square was 0.96. So generally, we cannot say from the MSE it's bad or good. It depends on the problem itself. While in R square, because it's normalized, well, we can see it X basically can explain much from Y. So we can use another type of model. So let's try 1, 2, 3, 4 and run it. So we can see the slope and the constant have slightly changed. We have worsened MSE while the R square is very close to it. Let's just try another one for 85. Okay, we have another model still worse than the other models that we've done before with the 42. Still, so the first model seems to be the best one. Let's give it another try. So 687. And this time, yeah, was the best by luck. Okay, and we have even captured 2 points exactly there. But be careful. Okay, so could be a warning sign that we could have an overfitting a problem. Okay, so if we have like a future data set beyond the testing data set, so we should be aware of that. Now, in next video, we will learn how to basically transfer the data.